Hello students, today we will continue to share about OFDMA scoring multiplexing multi-finger technology. In our next class, we mentioned that the core advantage of OFDMA technology is that it enables multi-user transmission without having to queue and compete like our Wi-Fi 5, which greatly improves our efficiency and reduces latency. It is particularly suitable for scenarios that require the transmission of a large number of small data packets, because each unit is relatively small, allowing for a large amount of simultaneous transmission. This is also a major breakthrough between Wi-Fi 5 and Wi-Fi 6. OFDMA technology makes Wi-Fi 6 perform exceptionally well in handling multiple users concurrently. It solves the issue of multi-user competition present in Wi-Fi 5. Then let's take another look. In Wi-Fi 6, the classification of different RUs allows bandwidth to be divided according to RUs. For example, in a 20 MHz bandwidth, we can divide it into 9 RUs. 9 RUs. This can support multiple users transmitting simultaneously, and if it's 40 MHz, it can further expand to support more users. In the maximum case, a 160 MHz bandwidth can support even more, providing greater concurrent transmission capability. This also involves the concept of orthogonal frequency division multiplexing, OFDM, which is a technology that transmits data by dividing the spectrum into multiple smaller frequency bands. Through this technology, Wi-Fi 6 can effectively support multi-user concurrent transmission, improving network efficiency. All right, next we will begin introducing the 802.11 MAC layer and its related technologies. First, it is important to note that the channel is shared by all stations. When a station needs to transmit data, a channel allocation mechanism is required. This mechanism might be somewhat difficult to understand, but it is essential to have an understanding of it, because this is crucial for us to explain this technology. The core of the channel allocation mechanism is how to avoid collisions. In the MAC layer, we have 2 coordination methods. One is the distributed coordination function, known as DCF. The other is called the point coordination function, known as PCF. Here, we will only focus on the distributed coordination function, which is DCF. DCF uses carrier sense multiple access with collision avoidance protocol, also known as CSMA-CA. Under this mechanism, each station needs to compete for the channel's usage rights before sending data. Specifically, if a station wants to send data, it first needs to check if the channel is idle. If it is idle, it can then request to use the channel. If the channel is already occupied by another station, it needs to wait. This is the principle of channel contention, ensuring that each station can orderly use the channel for data transmission. So what about CSMA? Let's take a closer look at what the CSMA-CA protocol is. CS stands for carrier sense, meaning that before sending data, a station needs to listen to the channel to ensure it is free, thereby reducing collisions. Now, MA stands for multiple access, indicating that the data sent by each station can be received by multiple stations simultaneously. Finally, collision avoidance is the design goal of this protocol. The purpose is to avoid wireless channel collisions through this effective mechanism. Since wireless resources are quite valuable, we want to prevent collisions. Therefore, the CSMA protocol uses this method to avoid collisions. Next, let's understand these detailed mechanisms. First, we need to understand the 2 important concepts of RTS and CTS, which are integral to our Wi-Fi 6. It is the core design for multi-user concurrency and collaborative work. You might have some impression that when we assume a terminal needs to communicate with an AP, how do they avoid conflicts? This is exactly the role of CTS. First, the terminal will send an RTS frame. It's called a request to send frame to the AP, indicating that it wants to use the channel, for example. Once the terminal sends an RTS frame to the AP, it requests to use the channel. When the AP receives the RTS frame. When the AP receives the RTS, it will respond by sending a frame called CTS, which stands for Clear to Send. This CTS frame is not sent individually, but is broadcasted so that other nearby devices, such as other terminals, PCs, or phones. After receiving the CTS frame, they will remain silent to avoid interfering with the data transmission of Terminal 1. Then, Terminal 1 can start sending data frames within the time allowed by the AP. The entire process uses the RTS-CTS mechanism to ensure that there is no conflict in channel usage. We previously mentioned the duration of data transmission and whether there is an acknowledgement frame, ACK, after sending. After sending data, the receiver needs to confirm receipt of the data. This is part of the RTS-CTS mechanism. Now, let's discuss a question. Is Wi-Fi communication simplex or duplex? It is. Half duplex, meaning during the data transmission process. It cannot send and receive simultaneously. After sending data, the device must wait for the acknowledgement, ACK, before it can receive data. Therefore, Wi-Fi does not support simultaneous sending and receiving of data. It can only complete sending and receiving at one point in time, not simultaneously. What needs special attention is that the wireless air interface is different from wired networks. Wireless communication is half duplex, not full duplex. This is an important characteristic of wireless communication. Through the RTS-CTS mechanism, we can avoid collisions of large data frames before sending data. It itself is a small data frame, which reduces the chance of collisions. However, there is a special point here. Who will send the RTS request first and who will send it later? If two devices send this request simultaneously, competition will occur, which will waste channel and bandwidth resources, leading to bandwidth loss issues. For example, suppose the AP's bandwidth is 100 megabits. Then it connects to the external network through a 100 megabit cable. If there is only one terminal connected, its maximum transmission rate is 100 megabits. But if there are two terminals, for example, two PCs connected to the AP, how the bandwidth will be allocated becomes very difficult to calculate because the allocation of bandwidth is influenced by various factors. For example, channel competition interference. Theoretically, this bandwidth will decrease, but it is difficult to predict accurately. During the course design phase, we discussed this issue multiple times with the R&D team, but there is still no precise calculation method. Therefore, we usually can only estimate based on experience. First, many AP manufacturers claim that their devices can support a large number of user connections, such as 512, 1024, or even 256 users. So, what exactly is the significance of this data? It is almost. In the field of IoT, these numbers might have some reference value because IoT devices generally have low power consumption and small bandwidth requirements, so a large capacity is acceptable. However, in the Wi-Fi domain, such numbers are almost meaningless. Why? Because in practical applications, even the busiest APs rarely support 100 users. Even if there are such cases, they only appear in specific locations, such as bus stations or high-speed rail stations, where APs might have a higher number of connections. However, their usage scenarios and requirements are vastly different from our office or home environments. For example, let's say at a high-speed rail station, we encounter a situation where we connect to Wi-Fi, but I can't open a web page. Then, when I check the AP, it already shows that 74 users are connected. This is a typical problem when we have multiple terminal devices connecting. The protocol will greatly increase the network burden even with only 2 devices. The number of requests is already quite significant. But if there are 100 terminal devices simultaneously initiating RTS requests, it will generate a large number of RTS/CTS frames, and these control frames consume a significant amount of bandwidth free, with their duration being in the microsecond range. The number transmitted per unit time is extremely large. Additionally, there are other management frames not mentioned. And if you include these frames, the waste of bandwidth resources becomes even more severe. Suppose the bandwidth is 100 megabits, and 2 terminals occupy 80 megabits of bandwidth. Then this results in a waste of 20 megabits, equivalent to a 20% bandwidth loss. This waste of bandwidth will significantly impact the efficiency of our network. Especially in a high concurrency scenario, if you want a single AP to carry higher bandwidth, assuming you need 5 megabits of bandwidth, then the number of users each AP can support may need to be limited to around 30. This is because the maximum bandwidth of each AP will limit the number of users it can support. If calculated this way, 150 megabits of bandwidth would be limited to about 30 users. Some manufacturers might claim that their APs can support more users. For example, 256 users, or say 512 users, but these figures are not very meaningful in practical applications because the bandwidth of a wireless network is limited, especially when multiple people are connected simultaneously. We cannot simply divide the bandwidth equally among each user, as high concurrency will lead to a decrease in bandwidth utilization. Wi-Fi 6 has made many optimizations in this regard. The goal is to reduce the adverse effects caused by multi-user concurrency. Although these improvements are not easily reflected directly at the data level yet, the user capacity data provided by manufacturers cannot accurately reflect the actual situation, because they do not take into account the interference and resource wastage in multi-user scenarios. The RTS and CTS protocols are conflict avoidance mechanisms, but the side effect they bring is that the more users there are, the more severe the bandwidth wastage becomes. For example, when there are 100 users, even if the total bandwidth of the AP is 100 MB/s, each user cannot enjoy 1 Mbps of bandwidth. The actual allocated bandwidth might only be a few KB or even less. Additionally, if multiple terminals send RPS requests simultaneously, it will further exacerbate bandwidth congestion, affecting the overall network performance. Today, we will end our discussion here. Students, if you're interested in Huawei's certification or Huawei's question bank, you can leave a comment below my video. I will also respond to everyone.